neutral alignment.
Okay, so this is a set of notes on arc length. Okay, so the arc length formula for parametrics and polars, not parametrics and polars, vector valued functions and parametrics is the same as the distance along the curve, which we got before. So if you go from t1 to t2, and then it's x prime of t squared plus y prime of t squared. So again, this is literally the integral of the speed over the interval from time 1 to time 2. This is not new information. So we have this and we're working with it. Okay, so that's vector valued functions and parametrics. That's the easy case. So we're going to look at now, what do we do if I have a rectangular function? Okay, so something that's like Cartesian, your typical function. Okay, so what we would have here is something like y equals f of x, and we're going to take this on some interval when x runs from a to b. So if x is from a to b on the domain, what is the length of this curve? Okay, so there's a bit of a strategy here that will lead us to a formula. We just let x be t. Okay, so we parameterize x. So this gives me that y of t is x at time t, which is just t, and x of t is t, so this is going to be the same thing as like f of x, right? So let me get a little bit of space there. Right, so this is the same as f of x. I'm sorry, that's not correct. Let's fix this a little bit. Y of t is the same thing as f of t, and since t and x are the same thing, that's f of x. There we go. And x of t is just straight up t, right? So this means that y prime of t is equivalent to f prime of x, and x prime of t is 1. Okay, so if we apply this into this formula, because we've correctly parameterized, then the arc length, okay, and we're going to ascribe that at time t1, x is at the value a, at time t2, x is at the value b. The x prime of t squared is just 1. Y prime of t squared is f prime of x squared. And the change with respect to t is the same as the change with respect to x. So if I have a rectangular function, this will actually give me the arc length over that interval. So this is the one that I use for vector values and parametrics. This is the one that I use for rectangulars. Let's get an example of this. Okay, so let's say we want to find the length of y equals x to the 3/2 on the interval when x is going from 0 to 4. So I need the derivative of this, right? So y prime of x is going to be 3/2 x to the 1/2, right? Because that's minus 1. So this means the length is going to be the integral, right, from 0 to 4 of the square root of 1 plus 3/2 x to the 1/2 squared dx, which works out as the interval from 0 to 4 of the square root of 1 plus 9/4 x dx. So this one you can actually kind of work out until we get to like the dead end here. Let u be 1 plus 9/4 x. That means that du dx is 9/4, which means that dx is 4 du over 9. Right, so changing the bounds of integration, putting a 0 in there makes this a 1. Putting a 4 in there should make this a 10, which now gives me u to the 1/2 times 4 du over 9. Right, so that's, let's see, 1/2 is going to become 2, or sorry, it's going to go to 3/2, right? So it's going to be u to the 3/2, right? So that's going to be 2/3 times 4/9 will be 8 over 27, u to the 3/2, and u is now running from 1 to 10. So this is 8 over 27 times 10 to the 3/2 minus 1, and that's a complete answer. It's not very satisfying. If you plug that into a calculator and you turn it into a decimal, that's going to be approximately 9.073. So the length along this curve, as x is running along that interval, is a little bit more than 9 units. Okay, so one of the things that's tricky about this is that a lot of these problems start putting a square root inside of an integral, which is very difficult to do the integration of. You'll find that a lot of the BC exam problems on this are either calculator active, and you'll end up with like a number like this in the end, or they're like a setup but do not solve the integral kind of problem. So that happens. All right, so we've dealt with vector valued functions, parametrics, and rectangulars. We still have to deal with how to deal with arc length and polar functions. Okay, so let's look at arc length and polar functions. Okay, so recall that x is our cosine theta and y is our sine theta. Now if you do some leveraging here, you're going to get dx d theta comes out as negative r sine theta plus dr d theta times cosine theta. Okay, and dy d theta is going to come out as r cosine theta plus dr d theta sine theta. Okay, so let's take a look at what happens here. If I take what's inside the formula, I take dx d theta squared plus dy d theta squared. This is going to give me like dr d theta squared, since I have it in both of these. Oh, that's this, times cosine squared theta, right? And then we get the minus 2 r sine theta cosine theta dr d theta. And then we square this guy, is going to give me plus r squared sine squared theta. Okay, and then when we play the same game with this one, we get dr d theta squared sine squared theta plus 2r sine theta cosine theta dr d theta, and then plus r squared cosine squared theta. Alright, so if I look at this, this here cancels with this here. So that clears out a whole bunch right away. And then I get some interesting stuff here. Like these two line up, right? So that's going to give me like a dr d theta squared, and these two line up plus r squared, right? And this is going to be times cosine squared theta, because I got one of those in each, plus sine squared theta, which we recognize as 1. So, what did we just prove? We proved that this can be written as that in terms of r. All right, so this is not something that I would want to have to do in the middle of the test, is to prove that all out. But what we just did is got a pretty simple formula for arc length. Because if I look at the original formula for arc length, I get t1 to t2, right? Square root x prime t squared plus y prime t squared dt. Well, this is x prime t, that's y prime t. And at t1, we're just going to say that our value is theta 1 to theta 2. And this got reduced to this, dr over d theta squared. I think normally the formula gets written backwards. It gets written as r squared plus dr d theta squared, right? So, and then this comes out as d theta. Okay, so this is the formula that we're going to use for polars. So another one that you should commit to memory. Let me clear this space out at the bottom. Take a look at how that works a little bit. So let's say we want to find the length of r equals 1 plus sine theta. When theta is running from 0 to 2 pi. So once around the cycle, right? So dr d theta is just clearly the cosine of theta. So the length should be the integral from 0 to 2 pi of the square root of 1 plus sine theta squared plus cosine theta squared d theta. So this becomes the integral from 0 to 2 of square root of 1 plus 2 sine theta plus sine squared theta plus cosine squared theta d theta, which that's just 1, right? So that's going to come out as the integral from 0 to 2 pi of square root of 2 plus 2 sine theta d theta, which the square root there causes some problems, but that's about as simple as we're going to get without some major intervention. If you throw that into the calculator, believe it or not, that is 8. That works out to be 8. So there you go. Arc length for vector valued functions, parametrics, rectangular functions, and polars.